Well, hello everyone. This is us, our final chapter of Math 141, final section, I should say. And we're going to deal with modelling with exponential functions, section 4.6. So let's get started. If you look at the list here, we're going to look at questions involving doubling. So these are typically population models where you start off with a certain number of creatures, insects or bacteria, whatever it might be, and they double after 4 years or 4 minutes. And you create a formula that will predict how many of this bacteria or animal, whatever it is, the population is modeling, will be present in 10 years from now, 20 years from now, and so on. Exponential growth models basically fall into population growth. Tells you it's a population of creatures and they grow, but this time the information isn't how long does it take for the population to double, it's how long does it take the population, well, not so much how long, let's phrase that better. You'll be told what the relative growth rate is. In other words, the population grows by 3% a year or 0.2% a year. So it tells you for 1 year what that growth would be. So they call this the relative growth rate, or normally just growth rate for short. And although the answer or the information is given in percentages, when we use that information, it's used as a decimal. So if it's 4%, we use 0.04 in our calculations. And exponential decay models are very similar to growth models. Their formulas, their creation is very similar, the math is. And the only difference is that the population is declining. So you have a population that's under stress and there's fewer of them next year than there was this year. So you would say that it may have a decay rate of 4%. We also use radioactive decay questions fall within that. And then we do Newton's law of cooling, which basically is a clever formula that tells you what the temperature of an object would be if you knew its original temperature and you know what the room temperature is, how long it would take to reach that room temperature and at any given moment of time. And it's used in such things as actually telling how long someone's been dead for. So let's begin with the first kind. So here's a story, question, puzzle, whatever you want to call it, involving a doubling story. So suppose there's 100 bacteria and their population doubles every 12 minutes. The two most common questions you're going to get, apart from create the formula, is how many bacteria will there be in an hour, in 20 minutes, in 4 days, that type of question. And then part B is going to be how long before there is 20,000 bacteria, 2,000 bacteria, whatever it might be. So the general formula for a doubling story, a population that doubles, is the number that you'll have after time t is given by n naught times 2 to the power of t over a. N naught is the initial population and a is the amount of time it takes for it to double. So in this story here, the formula that we're going to use is 100 because you start with 100 bacteria times 2 to the power of t over 12. So time is going to be in this story in minutes. Sometimes time is years, sometimes time is hours. Whatever it might be, in this case, we know it's minutes. So this is the guy that's going to generate all the other answers. So the answer to question A is how many bacteria after 1 hour. Well, I'm not going to put 1 there because remember we said it was minutes and 1 hour is 60 minutes. So that's 2 to the power of 60, right, minutes, divided by 12. And then at this point, you let the calculator take over. So it's going to be 100 times 2 to the power of, a little bracket around it, 60 divided by 12. And the answer, whoops, is that you're going to have 3,200 bacteria. Right, so you start off with 100. By the time an hour's gone by, if you don't kill them with some kind of insecticide or whatever you kill bacteria with, you're going to be down or up to 3,200. And if you left it another chunk of time, you could end up with millions, which brings me to question B. How long before there's 2,000 bacteria? Right, you begin each of these questions by stating the formula. Have you noticed that I've written 100 times that? If I didn't, if I just wrote 100 to the t over 12, you might mistake that as 1,002, right? To the power of t over 12. You could write it like that, and that would be a way to distinguish it. I'm using a dot, but yeah, write a bracket if you like. Now, in this second story, it's how long before there's 2,000 bacteria. So 2,000 bacteria goes there, and you've got 100 times 2 to the power of t over 12. Well, I'm going to divide both sides by 100, and I've got that. What I'm going to do now, because we've already seen questions where you have to solve exponential equations, is I'm going to use the fact that this is power of 2. So I'm going to do the log to the power base 2, right, of 20 is t over 12. Technically, I skipped a line there. Log to base 2 of 2 t over 12. And that gets me the log to base 2 of 20. And isn't log to base 2 of 2 to that power just gets you t over 12? And then to get t, I just multiply both sides by 12. Now, if the answer, or if the question just wants the answer, and they do not mention 2 decimal places, then there is your answer. Of course, you probably would want to know how long that is as a number, as a decimal. So let's figure out what the answer would be in two decimal places, let's say. So I want to calculate this. Now, you might have a clever calculator that can do log to base 2, but most of us don't. So I'm going to use the change in base formula. So log to base 2 of 20 is a log of 20 over the log of 2. And now I can get the answer. It's going to be 12 times log of 20 divided by log of 2. And the answer is about, let's say to 1 decimal place, is about 51.9 minutes, just shy of an hour. Okay, let's do another one of these doubling stories. Let's suppose that we have a new bug gets into Florida and it loves oranges. And the initial number of these bugs, the initial number was 24, right? So there was a crate, and inside this crate of bananas, whatever it is, there are 24 of these bugs who love oranges. These bugs double in population every 6 months. I would like to know how many bugs there's going to be in, say, 17 years, just a random number. And secondly, how long before there are 1,000,000 of them. See, if there's only a couple of thousand, one orchard, if that's what oranges grow in, might get a small reduction in the production of oranges because, there's lots of oranges and not that many bugs. But when you get 1,000,000 of them or 1,000,000,000 of them and they are not controlled, you're really going to have problems. So let's start by creating the formula. N of t is n naught times 2 to the power of t over a. Now, in our story, there was 24 bugs times 2 to the power of t over 6. And let's time be in months. Because of what I did there. So the first question is, how many of these bugs are there going to be in 17 years? So it's 2 to the power of 17 over 6. Let's see what that looks like. On my calculator then, 24 times 2 to the power of, put a little bracket around it, 17 divided by 6, close the brackets. There's going to be, to the nearest whole number, 171 bugs. You wouldn't even know that it entered the country, right? 179 bugs could hide easily in any orchard. You would just think, yeah, there's another weird bug. I wonder how long it takes to get 1,000,000. So the formula is 24 times 2 to t over 6. Well, you might think, oh, it'll take 1,000 years or something ridiculous amount, right? Well, maybe not. There's 1,000,000 goes here. 24 times, I'll do it that way, a little bit easier for me to keep track of things. So first thing I'm going to do is divide both sides by 24. And I'm not going to do anything else. I could calculate that as a decimal, but I'm just not going to. I'm going to take the log to base 2, both sides. There's 1,000,000 over 24. And if you take the log to base 2 of that, you get t over 6 because I'm cutting down on my work. And then you would multiply both sides. And you'd be looking at that guy. So 6 times a log to base 2 of 1,000,000 divided by 24. And that would be the exact value of the answer. Let's suppose I want to know what it is to nearest month, right? Nearest whole number of months. Then to get the log to base 2 of any fraction, it's going to be log to base 2, let's say of 1,000,000 over 24. I'm going to do it now. What's 1,000,000 over 24? 1, 2, 3, 4, 5, 6. Divided by 24. Let's try that again. There. 1 divided by 24 is about 41,666.7 roughly. Now, to get the base 2, I'm going to do a change in base formula. So that's log of 41,666.7 over the log of 2. And here it goes. We got 6 times the log of 41,666.7 divided by the log of 2. And the answer is only 92 months. 7.5 years. So you can see that even a small infestation of bugs, of larvae, butterfly, whatever the darn thing is, if it gets a niche market where nothing eats it, right? Because there isn't any creature going around that is specializing in eating these creatures, then they get a kind of free run to duplicate, and there's plenty of things to eat, and they just do well, and you end up with just far too many of them, and they cause damage. So that is the end of questions involving bubbling. We're now going to do exponential growth models. Well, in these stories, you're given an initial population typically, and then you're given a relative growth rate. And from that, you can actually calculate, create a model which can then be used to calculate future populations after certain times. So the generic formula is NT N naught E to the RT. N naught is the initial population. So how many do you start with? Right? R is called the relative growth rate, or just growth rate for short. But you convert it to a decimal. So if they tell you it's 4%, it's 0.04. And T is time. And time can be minutes, seconds, hours, days, whatever the question tells you it is. So we are going to create this model, and then we're going to be asked to answer things like, what will the population size be in 10 years? How long before there's a million of them? Whatever it might be. So let's suppose in this story that there's a town. And this town has a population of 3,200 people. And its growth rate is 3% per year. And the questions might be, how many people will be in this population, right? This town in 20 years. Or B might be, how long before there are 100,000 people in this town? Well, it'd probably be a city by then. And not all small towns turn into cities. Some small towns basically stay as small towns for their entire life. Some become ghost towns and disappear. And a few, only a few, turn into cities. They just get bigger and bigger. And there's reasons for why that might happen. Maybe the town is in a very fortunate location, either geographically, or maybe they discover some rich mineral, gold or whatever, and populations increase quickly in those situations. So let's create the formula for it. The population growth model is its fancy name. Well, there's 3,200 people, E to 0.03 T. So from now on, that guy is going to be our population model. So in question A, you're being asked how many people will be in this town in 20 years. And there's your calculation. 3,200 E to the power of 0.03 times 20. 20 years. So I've got my calculator. And we go 3,200 times e to the power of 0.03, and I better put brackets around that, 0.03 times 20. And that town has only grown to roughly that. Well, actually, to the nearest whole number, 5,831. Yeah. Now, I asked how long before there are 100,000 people. So you begin with your formula. And you make that 100,000. And now you are going to solve this exponential equation. First thing you're going to do is divide both sides by 3,200. Then you're going to take the natural log of both sides. And the natural log of this guy is 0.03t. I want to save a line of working. And then I'll divide both sides by 0.03. And that is going to be our answer. So here goes. The natural log of 100,000 divided by 3,200 divided by 0.03, and the answer is to one decimal place 114.7 years. Well, you know, America's got, I'm sure it's got quite a few places or cities of 100,000 or more that started off as very small villages and has grown to that size. That's pretty rare that that happens, but that does happen. In this particular scenario, it would take about 115 years to become a city. Now, suppose we make this question a bit trickier. Suppose I tell you that you start with 80 purple, oh, what shall we have? Bears. That's all there is, 80 of them. Very rare, almost extinct, right? But then they protect them, right? They put fences around it, they protect it from poachers. And because they did such a good job, in 20 years, the population increased to 250. So, I mean, there's still not a lot, but there's more than there used to be. First thing is create a model to predict how many bears in 10 years. Just how many bears. We don't need 10 years. In B, now we'll use the model to predict how many bears in 50 years. And the third question is how long before there are 1,000 bears. So it's an exponential growth story. So generic formula is n naught e to the RT, which is fine. What do we know? Well, you know that you're going to start with 80 bears. But what is missing from this question is the relative growth rate. They didn't tell me that the bears grow at 2% a year or anything else. They told me that in 20 years, the population had increased to 250. So I can put 250 here. And T is 20, right? In 20 years. So 20, R times 20, let's call it 20R. So if I can solve this exponential equation, I will be able to find R. And R, right, is the relative growth rate. Well, you divide both sides by 80. Right, what do you think I'm going to do next? We've done very similar questions in the past. What do you think I'm going to do next? I'm going to take natural log. And taking the natural log of this guy gets you 20R. I'm then going to divide both sides by 20. And there we are. We've got the relative growth rate. Let's see what it is. It's the natural log of 250 divided by 80. It's that bit. Divided by 20. And so the relative growth rate is 0.057, let's say 83 decimal places. Or about 5.7% per year. That's a pretty healthy growth rate. We now can return to our generic equation. That's this one. You still start with 80, but now you got that guy. So once you have got your population growth model, you can then use it to predict how many bears in 50 years, which is what I'm going to do next. Population is 80 e to 0.017. And we are going to find out what the population will be in 50 years if they continued at the rate that they have done so far. Be 80 e to the 0.057 times 50. So that's really just a plug and chug on the calculator. You got 80 times e to the power, the little bracket around it, 0.057 times 50. And the number of bears in 50 years will have grown to 1,383 to nearest whole number. And question C is, how long before there's going to be 1,000 bears? So like every other question like this, you start with the formula, right? That guy. Now you put 1,000 here and you solve for t. You divide both sides by 80. You take the natural log of both sides. If you look back at the other questions, you'll see that I'm pretty much employing the same method, the same process. I'm doing the same things each time. For instance, my last step here will be to divide both sides by 0.057 this time. That's this guy over A divided by 0.057. I'll put the calculator. And we will have the log of 1,000 divided by 80. Is that bit? And then divided by 0.057. And the answer that we would get is about 44.3 years. Okay, let's have a look at some homework questions involving exponential growth. So let's see what we can get here. I got anything? Not yet. Let me see if I can open up something. How about here? That'll work. Okay. Okay, so here we are. This is question 8 homework. Some bullfrogs were introduced into a small pond. The graph shows bullfrogs' population for the next few years, and assuming that the population grows exponentially. Now, in this question, you're going to start with a graph, so that's a little bit different. So we can look at the answers here. You can see what's happened. You notice that at year 0, this beginning, is 100. That's where that comes from. Now, if you notice the next guy is at 2 years, the population is now 225 bullfrogs. So if you're wondering where does this 0.4055 come from, that's essentially the growth rate. So let's see if we can create that. The number of frogs, n of t, is n naught e to the rt. We know that the initial population of frogs was, and I've now forgotten it, I believe it was 100, but I'll double check. Yeah, was 100. And that's e, right, to the rt. Now, in 2 years, there's 225 frogs. So 225 goes here. And e to the rt is e to the r times 2, which is 2r. So what we're going to solve is for r. We're going to find the relative growth rate. So 225 over 100. So I divide both sides by 100. I take the natural log of both sides. And the natural log of e to the 2r is 2r. I will then divide both sides by 2 to get r. And on my calculator, we get the natural log of 225 divided by 100, which is that guy, divided by 2. And we get 0.4054, which if you remember the answer that you saw, it was that guy. So the population model is now going to be, instead of n naught 100, e to the r, which is that guy, t. Now, once you have this formula, you can then answer the 2 standard questions. How many bullfrogs in 10 years, 20 years, 80 years? How long before there's 5,000 bullfrogs or 5 million bullfrogs? You can solve both those questions now that you have this formula. Let's see what else we can. Okay, there we go. Try to get my mouse to connect. Oh, where is it? I've lost it. Okay. You bear with me for a few moments. See if we can figure out why my mouse is not working. Oh, there, came back. Okay, so let's return now. Have a look at that guy there. And yeah, that's pretty standard. And we have covered that. Okay. Just want to make sure that we're in the right place. Okay. Looks like maybe the battery is going on my poor little mouse. It's had a hard day. See if I can figure out what's not. It's not that. Okay, I don't know how long this thing's going to last, but I'll try to keep going. So that's us finished exponential growth models. Let's look at exponential decay models. These are population models where the population, instead of increasing, decreases, and we call that decay when something decreases. There are two basic kinds. There's population of animals, people, and there's radioactive decay. So let's do, as my first example, let's do a population that's under stress. So let's suppose that there are 5,000 pink elephants. Just being silly today. You didn't know that. They're very rare, pink elephants. Not everyone gets to see one. But what you also don't know is that they're dying off. Yep. And they have a relative decay rate of 4%. In other words, they are going to decrease by 4% every year. So let's see what the model would that be. Well, it's N naught E to the negative RT. When things decrease, have a negative growth rate, in this case, a decay rate. That's what we call it when it's negative. You get 5,000 elephants, pink ones, E to the negative 0.04 T. That's the model. Now, once that's been done, the good news is that most of the other kinds of questions are very straightforward. One of them will be, how many elephants in 20 years? So if the elephants keep, getting fewer and fewer, what's going to happen? Well, you're going to have less, of course, but how many will you have in 20 years? So the number in 20 years is going to be 5,000 times E to negative 0.04 times 20. So that's really just a plug and chug on my calculator. So we'll go like this. It's going to be 5,000 times E. Let's do that version of E. E to the power of, put a bracket around it, negative, notice I'm using the bottom, that guy there, negative 0.04 times 20. And that is 2,247 to the nearest whole number. That's more than half the elephants, right? There's fewer than half. I guess that's a better way of saying it. That's not good. If that continues, they're going to go extinct. So question B might be, how long before there is 100 elephants? Well, we know the population model. It's that guy. I'd like to get 100 elephants. Well, I wouldn't like to get it. I'd like to know how long it would take for that to happen. Okay, hopefully you are very familiar with this type of equation. It's going to involve the same 3 steps that I think the last 8 questions have done. Divide. In this case, both sides by 5,000. Take the natural log of both sides. And the natural log of this guy is that. Now to get t, you take the log and you divide it by negative 0.04. We are going to be looking at, let's clear it, the natural log 100 divided by 5,000 divided by negative 0.04, and that's about 97.8 years. So we could say with a reasonable degree of confidence that in about 100 years, they're virtually extinct. By the time you get to only 100 of an animal, the genetic diversity is not good. So even if you try and do a breeding program with those, it becomes really difficult. You'd have to actually go and capture them all, put them in some kind of protective environment, and and selectively breed them to try and increase the numbers. And it has been possible to do that. But if an animal like an elephant takes a long, long time just to rear one baby to the point where it's independent, you are not going to be able to get any kind of growth out of them that's meaningful unless you have a very long term, couple of 100 years time scale. It doesn't mean you shouldn't do it. It just means you have to be really patient if you do decide to try and improve on that situation. Now, the second kind of radioactive decay, decay models are radioactive decay. So let me say that sentence again. The second kind of population decay models is radioactive decay models. So I'm going to try, if I can, to find you one to do with carbon-14 data. Right? So the question that we're going to be looking at is question 11. So let me jump over there and show you what it looks like. A wooden artifact from an ancient tomb contains 55% of its carbon-14. Right, carbon-14 is an isotope of carbon. It's still carbon, but it's a special type of carbon. Very often it has more or less neutrons than it typically would have. And it tends to be very often that these are radioactive, and that's another way of saying they're unstable and they break apart. Whereas the normal carbon would last a lot longer and probably not decay at all in any meaningful way. Now, if we read on, it gives us this thing called the half-life. The half-life of carbon-14 is 5,730 years. That is a long time. So if you had 100 grams of this pure carbon-14, that's not the way it works, but suppose you had that. If you came back 5,730 years, you'd still have 50 grams of it left, right? It's still a sizable amount, a measurable amount. So we're being asked to find the decay rate. Wow, 6 decimal places. Let's see how that works then. Well, we know the model. n of t is equal to n naught e to the negative RT, right? That is a radioactive decay model. There isn't any mention of the initial amount. We'll forget about that for the time being. That's not the initial amount. That's how much was left in some time in the future. We don't know yet because that's going to be a later question. Let's just get the model using this piece of information here. So I'm going to say that N naught is 100%, right? Pure carbon-14. And it's equal to that guy. Now, if you tell me its half-life is 5,730 years, you're telling me that you'll have 50% left, right? Half of 100 is that. And it's going to take you 5,730 years. So R times that number gets you that. So there we are. Do you recognize the exponential equations that we've been doing for ages, it seems now? So let's go through the process. Divide both sides. You got that. Take the natural log of both sides. I can do that. I'll call it a half. It's quicker. And now I'm going to divide both sides by negative 5,730. And we will have the relative growth rate. And it's ln of 0.5, that's what a half is, divided by negative 5,730 into 6 decimal places. Well, let's see how that works. 1.20968 and some other stuff. And then it has this funny e to the negative 4. That makes this thing 1.20968 times 10 to the negative 4. It's called scientific notation. And if you want to turn this into a decimal, and essentially what you do is you start with 4 zeros, including this 0 at the front. That takes care of that. And then you write all the other digits after that. But we were asked to get it to 6. So there's 3, 4, 5, 6. That rounds up to a 1. So the relative decay rate is 0.000121. So n of t is going to be 100, right? The whole amount, e to the negative 0.000121 t. And that's us got by that part of the question. So what we're going to do now is that piece of wood that they found that only had 55% of the carbon-14 left. Let's find out how old it is. N of t is 100 e to the negative 0.123121 t. And we have 55% of it. 55 there. And we are trying to solve for t. Now you look at that guy, that should be deja vu, because it is. It's going to be divide, natural log divide. Divide both sides by 100. Take the natural log of both sides. That guy is easy, so I'll turn him into a decimal. Natural log of this guy can be shortened down to that. And then divide both sides by negative 0.123121. And that'll get you the t. So let's see how old that piece of wood is. The natural log of 0.55 divided by negative 0.123 121. And the answer is 4,940 years to the nearest whole number. Actually, 41 years to the nearest whole number. So it's almost 5,000 years old. So we can now, for organic material, things that have carbon in them at least, if we find remnants of them, we can analyze them in a machine that will tell us how much of the carbon-14 is present. And from that, you do a calculation just like this, and you will have its age. And that is the end of exponential decay. So the last guy that we're going to deal with is Newton's law of cooling. So let's show you. There's only, I think, 2 questions using Newton's law of cooling. Here it is, up the top. So the temperature after time t of a cooling bowl of soup is 68 plus 139 E negative 0.05 T. And it's going to be very quick. Essentially what you've got, here's a little story and we'll come back to that. You've got a hot cup of tea, right? And that hot cup of tea is in a room. Let's say it's sitting on a table in a room. Room temperature is 68 degrees. This hot liquid here is actually 190, 207 degrees, right? And you would, I'm assuming you would like to know, as it cools down, what the temperature would be in 10 minutes, 20 minutes, 50 minutes, you know. When would the temperature get to 80? Now, because the room temperature is 68, this won't keep cooling through time and you end up with a block of ice. It'll finish off its life at room temperature, right? Things just cool down to room temperature. And this quite clever model, this formula, is called Newton's law of cooling because he's the guy who figured it out. So, first question they asked you is, what's the initial temperature of that soup? Now, I've told you it's 207. Let's show you how I can find out. The initial temperature is the temperature at time 0. So 68 plus 139 e to the power of negative 0.05 times 0. And that's 68 plus 139 times e to the 0. But e to the 0 is 1. So that's 68 plus 139. And I hope that's 207, as I first predicted. Now, there are 2 other questions that you're going to deal with. And the first one is going to be something like, what's the temperature of this liquid in 20 minutes? Let's say time t is in minutes. Well, here's our formula. You want to know what the temperature is in 20 minutes? It's a plug and chug. Just replace the t by 20. And then very carefully, make sure you hit the buttons in the right order and all that. And you should be able to get it. Let's see, 68 plus 139 times e to the power of negative 0.05 times 20. And that's roughly 119.1 degrees. Just getting there. It's 119 degrees. Now, the last type of question that you're going to get is how long. So, how long before, right, the temperature reaches, let's pick a number. Since the temperature in the room is 68, let's say 75 degrees. So how long would it you have to wait until you get to that temperature? So you begin with your model. And our quest is to figure out what T is. So that's 75. Okay, a little bit different, but not that different. I think it really just has one extra line. You're looking at that and you're thinking, how am I going to find T? It's all about as long as you do it to both sides, it's okay, roll. And it's also about which thing you do first, what you do second, what you do last. Well, I would subtract 68 from both sides, and that would leave me with 7. I would then divide both sides by 139. What do you think I'm going to do to both sides now? I'll give you a few moments to think about it. What are we going to do to both sides now? Yep, we're going to take natural log of both sides. And taking the natural log of that guy, using the shortcut, you would eventually get that. And then last but not least, you divide by both sides by negative 0.05. And I go your calculator, and we'll see how long that will take. The natural log of 7 divided by 139. Divide that by negative 0.05, and the answer is about 59.8 minutes. In other words, roughly an hour. Now, the last question that you have in your homework in this section involves you watching a video, and I won't take anything away. I'll let you just look at it, and hopefully you'll be able to create your own Newton's law of cooling and use it to do as they do in CSI when they measure the temperature of a body, a dead person in a room. What they do is they find the room temperature, right? What's the thermostat say it is, and then they do what the body temperature is, and they can do some calculations, and they can come up with how long that person has been since when they died. And that is us. We are finished. So hopefully this has been an interesting and productive quarter for you. Bye bye for now.